Hello everyone and welcome to this new video in which I'm going to talk about hyperparameter optimization, and I'm going to show you certain libraries in Python using which you can do hyperparameter optimization. So it's very important because you have invested a lot of time in feature engineering and now you have come up with some kind of model that fits your problem, and now you want to find the best hyperparameters without investing a lot of time in manual tuning. So hyperparameter optimization can be done in many different ways. In my book I have dedicated a chapter, so if you have bought my book you can also go through the hyperparameter chapter there, hyperparameter optimization chapter, and I will be borrowing some of the stuff from the book in this video, and I'm also going to show you some new stuff that I have not discussed in the book. So hyperparameter optimization is like you have built certain features for your dataset and you have found a model, and now you want to find the best let's say the best learning rate. That would be a hyperparameter. Or you can also use it for neural networks. When you have neural networks you have to find the appropriate number of layers or some parameters inside the layers, right? So you can use it for that purpose too. So one of the easiest approach of hyperparameter optimization is using a kind of a grid, and that is known as grid search. So let's start with grid search. And before we begin, we also need some kind of data set. So let's see what kind of data set we have. So this is one of the data sets that we will be using. It's called mobile price classification. So what you're provided with is different features of mobile, and you have to predict a price range. So price range can be 0, 1, 2, 3. 0 is low cost, medium cost, high cost, very high cost. Okay, so these are the different categories that you have to predict. So it becomes a kind of a classification problem. And you see, like here, if I look at the distribution of labels, it's same for all different classes. So the number of samples for all classes are equal. So what we are going to do is we're going to take this data set and build different types of hyperparameter optimization, use different types of hyperparameter optimization libraries and see what happens. This is an easy data set, so this is not very difficult, so we might be able to find optimal hyperparameters very easily. So let's see. So here I have created I have downloaded this file called mobile_train.csv, in which you have like the different features. And so we won't be doing any kind of feature engineering in this tutorial. We will just be doing hyperparameter optimization. That's it. And I put it in the input folder, and I have created another folder called src or source, and inside that I have created a file called grid search. So one of the things that you have to remember, that you have to do everything inside a cross-validation loop. That's it. You have to do everything inside a cross-validation loop, and as long as you do that, you are not overfitting the model. So let's import a few file libraries. So we would need pandas, and to read the CSV we need numpy. Maybe we need numpy. Let's just import it. And we need some kind of model. So in this particular tutorial we will be using random forest just for the sake of it. So you can use any model that you want. Maybe in the end I will show you how to tune some parameters of neural network. So from sklearn import ensemble, and then we would also need some kind of metrics. So from sklearn import metrics, and you would also need kind of like create cross-validation folds, right? So from sklearn import model selection. So we have all these things. Now we can probably start with reading the dataset first. Okay, So let's read the dataset. Mobile train.csv. So this is our dataset. We don't have to do a lot of pre-processing on it. So what we have to do is create a training and create training features and targets. So X is my training features. So I can just do so in the dataset we don't have any kind of ID columns, so we just have a target column and all the others are features. So I can just do df.drop price range, which is the target column, x is equal to 1, okay, dot values. So I have created a numpy array of all the features, and similarly I have targets, which is df dot price range dot values. Okay, and now what you can do is you can just do a simple grid search on some parameters of the model that you choose. So let's choose a model. So I will say my model is the classifier is ensemble dot random forest classifier, and I will set a parameter of njobs to -1, so it's going to use all the cores of my machine. And then you will specify some kind of grid of parameters, so param grids, so which is a dictionary, and inside this dictionary you have the different parameters. So let's say one of the parameters of random forest is number of estimators, right? So we will set some kind of values there, 100, 200, 300, 400. So it's going to try all of them. And one of the parameters is max depth. So you can set some values there too, 1, 3, 5, 7. And let's say we want to tune one more parameter called criterion, and it can have categorical values like Gini or entropy. Okay, so we got the parameter grid, and now we want to do some kind of grid search on this. And scikit-learn provides you with a way you can do grid search with a cross validation. So you can also provide your own cross validation to the function, but we won't do that. We will just use a simple cross validation. And let's first import grid search cv. So grid search cv is going to do grid search with cross validation, and you have a estimator parameter. So estimator here is your classifier. The next thing that you do is you have a param grid parameter, and here we have the same name, param grid, the grid of parameters. And then you have a kind of a scoring strategy. So here, since we have all the classes have the same number of samples, we can use accuracy. And then we can define some kind of verbose. So let's say 10. And njobs, we have already said that njob should be -1 for the random forest. So here we are using only one core, and cv equal to 5. So that's doing the 5-fold cv. So this is not even stratified fold, so you should probably do stratified folds. So this is like one way of doing hyperparameter optimization, and you can just call the model fit function xy. Okay, and now it can return you the best parameters. So let's try fitting it first. So one thing that you should know that here, if you don't specify cv equal to 5, it's still going to be 5-fold cv. And if you have categories as targets, then it's going to use stratified k-fold. Otherwise it's going to use or binary classification, then it's going to use stratified k-fold automatically, so you don't have to worry about that. And now you can probably, let's train it, let's see if it works. So I'll go to the source folder and Python grid search. So it seems to be working, and you can see that it's printing some kind of score, and that's your accuracy score. So you can also replace it with some kind of function. So you can use the make scorer function from scikit-learn, and you can pass it through. So you can change whatever kind of scoring you want to do. So it seems to be going pretty strong. We have already seen 0.865, and now the next thing that you want to do is you want to print the parameters, right? Print the best parameters. So what you can do is you can say model dot best score will give you the best score, and you can also print model dot best params underscore best estimator underscore dot get params. So this will give you the best parameters of the estimator. So let's see. So this is going to take a while, because so what's it doing is, let's imagine a for loop, and that's what it's doing, and for every value here, every combination, it's trying 5-fold CV. So this takes a lot of time. So let me see if we can reduce some of the stuff. So maybe just try 2 estimators and 2 depths, and let's remove the criterion for now, and maybe it's faster. Oh, it's done. So it took 1.5 minutes. So let's run it again and see how much time it takes now. So you see, like now it went quite fast, didn't take much time, but also your accuracy is very low. So this is the best score that it has printed, and these are the parameters of your model. The best parameters of the model that it found. So it found like n estimators. So here it's printing everything. You don't need to care about everything. You need to care only about the 3 parameters: criterion, max depth, and n estimators. So this is like one of the ways of doing hyperparameter tuning. So another way of doing hyperparameter tuning is using a random search. So random search, what happens in random search, we select a combination of parameters randomly, and then we calculate the cross validation score. So everything that we have discussed here remains same, except instead of grid search CV, we now use randomized search CV, and everything else remains the same. So you have, instead of param grid, you can specify here, you have to specify some kind of distribution of parameters. So you can instead of like this list, we can write np dot a range 100, 1500, 100. Okay, so between 100 to 1500 everything, and we forgot a comma. Not everything, but with a step of 100. So np dot a range 1 to 20. Okay, so everything else remains the same. You also need to specify here number of iterations. So if I specify 10 iterations, then it's going to do random search 10 times, and that's it, and everything else can remain the same. So let's try this one. So I'm just doing 10 iterations for now, with an iter equal to 10. Okay, so it says that fitting 5 folds for each of 10 candidates, totaling 50 fits. So you see, like, this is also a little bit more expensive, but it's not as expensive as grid search. So grid search will take much longer because it has to evaluate everything in the grid, and right now if you see the size of this grid, it's huge. There are many different values compared to our previous one, but random search is not going to evaluate all of them, it's just going to evaluate some of them randomly. Okay, let's see how much time this takes now. So this took 1.3 minutes, and it gave a score of 0.885. So now you can see like the max step was 15, criterion was entropy, number of estimators was 600. So that's what we got from our parameter grid or distribution of parameters. So this was random search and the previous one was grid search. So all you need to do is specify a grid of parameters. So there's many things that you can do here. So one of the things is you can also do the same thing with some kind of custom scoring. So you can have a custom scoring method like which is not available in scikit-learn. Let's say you have your own method, and you can also use certain kind of pipelines. So here, if I don't really need to scale the data for random forest, but let's say I scale the data from scikit-learn import pre-processing, or I can also kind of like create some kind of decomposition. So let's do that instead, decomposition. And we also scale before that, so we do need to scale the data. So okay, so now, and we also import one more thing called pipeline. Okay, so now you have everything imported, and now what we can do is we have to create some kind of pipeline. So let's say we define a variable called scl, which is pre-processing dot standard scalar. Okay, and we have PCA. We do some kind of PCA decomposition on the data. So decomposition dot PCA, and we don't define the number of components. And then we have the classifier. So now you when you have these three things, your classifier, let's call it RF, random forest. So now your classifier is not the random forest, but a pipeline or like a sequence of these three things. So I can just do pipeline dot pipeline, and inside this I define a list. So let's say it looks something like this. Okay, and what you have, you first name what you're doing. So scaling. Okay, and scaling will use scl. The second thing that you want to do is do the decomposition. So PCA, and this is going to use PCA. And the third thing is your model itself, which is random forest RF, and this will be RF. So this becomes your pipeline, and now you have to change the param grid a little bit. So instead of let's say we also need to find out the number of components and components in PCA. So what you have to do is you have to add PCA in front of it. So this name that you have chosen, underscore underscore, so 2 underscores and then n components, and you can say the components can be anywhere in this range, let's say from 5 to 10 maybe. And then you have the other parameters. So here you have to do the same, RF underscore underscore. So this is the value of key in this list of tuples. So this RF. Okay, and now you can also write your own custom scoring, but we are not going to do that. So this remains the same, and then we run it and see how much time it takes now. So yeah, I'm calling it grid search, but it's not grid search anymore, it's random search. So let's see how much time this one takes. So now it has finished and given us a very bad score, obviously, because the pipeline is not good. So now you can see like you have these different steps. Okay, and inside this you are getting a bunch of parameters. So scaling also has different parameters that you can see, and then you also have the PCA, then you have RF in the end. So this is what you can use in case of using pipelines when you have different steps. But I mean, the score is not good for this one because I use something that I shouldn't have. But this is how it's done. And now we can go to a much better way of doing hyperparameter optimization, which is using Bayesian search. Okay, some kind of Bayesian optimization. So one of the libraries called scikit-optimize provides you with a way to do Bayesian optimization with Gaussian process, and that's something that you can use. So I'm going to create a new file for that and call it maybe should I do it in the same file? Then I need to change the name of this file, so just search.py. Let's do it in the same file. So what you need to do is you need to create a function called optimize function. So that's the first thing that you need to do. So optimize, and the optimize function, so you have to take a look at this function called gp minimize. So that's what we will be using. And then in this function should take a callable, which is the function to minimize. So that's our optimize function. It should take a single list of parameters and return the objective value. So that's what your optimize function should do. It should take a single list of parameters and return a value. So instead of taking it a list of values, which is params, right, we can also make it take a few more arguments, maybe param names, the names of the parameters, some x and some y, which is where x is our features and y is our target. And now what I do is I convert params to a dictionary. So dict zip param names comma params. So here I have converted it to a dictionary of parameters. So where my key is the name of the parameter, and the second one is the parameter value itself. So this is done. Now we can have a model. So here I'm not going to show you. So I mean, this thing probably is something that you cannot use if you are tuning parameters of multiple things here, but in our case we are only tuning the parameter of one single model, and this will take a dictionary. So now you don't need to specify the parameters, but it has already been done. Okay, and then you have to do all the k-fold stuff on your own. So model selection dot stratified k-fold, yeah, and you can have the number of splits is 5. So this is one of the things, and create a list of metrics. So here we will be calculating accuracies, and you can say for idx in kf dot split x comma y. So here capital X is x and small y is y, and then you split the data set. So you have to find train IDX, train indices, test indices. You can also call it valid indices. So test is here validation data. So you have x train, which is equal to x train IDX, and you have y train, which is y train IDX, and you have the same thing for, not the same thing but a similar thing for x test and y test, xy test and test IDX. Okay, so we have split the data. Now what we want to do is we want to fit the model first. So model dot fit, here it will be x train and y train, and then you create some kind of predictions. So we are very flexible here. Now we can also have probabilities instead of actual prediction, but here we just need prediction because we assume that we are using a 0.5 threshold. So predict x test, and then you calculate some kind of accuracy, call it fold accuracy of this fold. So metrics dot accuracy score and y test and preds. Okay, and you found this accuracy. Now append it to our accuracies list. Accuracies dot append full accuracy. Okay, and now you, in the end, you have to return it. To return it, you don't have to return the actual value. So remember, the function is called gp underscore minimize, right? So you have to minimize this value. So what will you minimize is return -1 into np dot mean of accuracies. So you are returning negative of the mean of accuracy. So if you have to like minimize log loss, then you should not multiply by -1 because that's already lower is better. And here what I've done here is a little bit interesting. So I've converted the parameters to a dictionary of parameters and input in the model itself. But now if you have number of different steps, you have to filter the parameters accordingly, parameter names and parameters accordingly. Otherwise this won't work. This won't work all the time. So you have to do it yourself. So now we need to define some kind of space of parameters that we need to search. So let me just get rid of all this. I don't need all this stuff. Okay, so our optimization function should accept only one value, one argument. So our optimization function can also be written as, so let's see, we import from functools, import partial. So now we write optimization function is equal to partial, and then inside that you have sorry, optimize, which is your function, and some more things. So param names, you specify some param names, we will do that now. And you have x, which is x, and y equals y. So what are param names? So param names are different parameters that we want to optimize, and they come in a sequence. So first of all, we will define some kind of parameter space. So when you're using skopt or scikit optimize, you have to define this parameter space, and space can take different kinds of variables. So this space can be real numbers, integers, or it can be categorical space. So if you look at the documentation of skopt, you have space.categorical, space.integer, space.real. So that's all we actually need. So we don't need anything more than real, categorical, or integer, right? So I'm going to import from skopt, import space, and here we define this space. So order is important, order of how you define these variables, and that will be clear after a few more lines of code. So space.integer, the first one, let's say between 3 and 15, and the name is max depth. Then again you have space.integer 100 to 600, and your name is an estimators. Okay, and maybe we can define a real number. So space dot real and inside this you can have something 0.011, name is number of features. So what is it called, max features. And how to choose, you need some kind of prior, which is, let's say, choose from uniform distribution. We can also add space.categorical. Then you have these choices, so Gini or entropy. Entropy, and here the name is criterion. Okay, so you have defined this list of parameter spaces now, and in the same sequence you have to define the param names. That's how we are using it here. So you don't really need to do that if you don't want to do it. So max depth, and estimators, criterion, and max features. So now if you have a standard scalar or some kind of other pre-processing or some other model, something like that, so you can also define it here sequentially. And then you just have to remember that in the function here, in the optimize function, you have to take them back from this params argument in the same sequence. That's it. And param names here is param names. So we have the optimization function now, and now we want to just run the gp minimize function. So we can write here result gp underscore minimize. So we also need to import it from opt import gp minimize. So, and here we can write the optimization function, which is the first argument, dimensions, which is the second argument. So dimensions is your parameter space, and then you have number of calls you have to specify. So let's say 15 calls, number of random starts, 10 random starts, let's say, and verbosity. So I'll just set it to maximum. So once you have that, you can also print the best parameters. So if you do a print like a dictionary, let's say, and you have param names and result dot x as values, so that's your best parameters. Let's run this and see what happens. So you can see in the verbose, you can see like it's evaluating different parameters now. So now we are getting a current minimum of 0.89, which is much better than what we got earlier using grid search or random search. So let's let it run for some time and see what happens in the end. So it has finished, but we got an error in the end. So let's take a look at that error. Okay, so I think it should be dict, and then I need a zip. Let's run it again just to see the last bit. Should not take a lot of time. So now we see that our max features are 0.69, so 69% features. No, sorry, the value of this argument is 0.69, and criterion is Gini, number of estimators is 339, and maximum depth of 8, and it reaches a accuracy of 89.75%. So this is one more way of doing hyperparameter tuning. So you just need to remember that the values, so you create these two lists and then create a dictionary here, and from here things will change a little bit if you are using something complicated. So like if you're using, not complicated, but if you're using like a pipeline, or using something different, something else, like some kind of trying to find parameter of another model and trying to combine it with this one, so then you have to take care of a few things. But this is how it works in general. Another important library for hyperparameter optimization is Hyperopt. So let's take a look at Hyperopt. So Hyperopt uses tree Parson estimators, if I'm not wrong, TPE, tree structured Parson estimators, to find the most optimal hyperparameters. So what we are going to do is, first we are going to import a few things for Hyperopt. So from Hyperopt, import hp fmin, the function for minimization, TPE, and trials. Okay, so we have that, and one thing that you have to remember now is, instead of param names, your params is a dictionary itself anyways, so we don't need param names at all, and everything inside this function, this optimize function, will remain the same. So when you're moving from skopt to hyperopt, it's as easy as that. Everything remains the same. And now you have to define the parameter space. So to define the parameter space, you have to actually use a dictionary here. So let's convert it to a dictionary. So we have this one here and this one here, and now how we define this dictionary here is you have the name, obviously. So let's take this name and convert. We're just converting it to a simple dictionary first of all, and then we will use Hyperopt spaces. So criterion and this max features. Okay, so we have max features here, and now you have to use hyperparameter spaces. So in this one it changes a little bit. So you have, instead of integer, you have hp dot q uniform. So you can read more about the many different types available, so you can read about them in the Hyperopt documentation. I'm not going into details there. For integers, if you have to use, you can use q uniform. So you have to specify max depth, the name, and then you have the ranges, so 3 to 15 to 1. So you can also see in this q uniform. Okay, it's not working for me here, but you can check out documentation if you want. And similarly, you have the number of estimators, which is also integer, so you can use q uniform again. And hp.q uniform, let me find out the documentation for it. Hyperopt q uniform hyperopt. Let's see if we can find it. Q uniform. So you have the low value, you have the high value, and you have the value of Q. Okay. Yeah, okay, so that's what I was checking. I forgot. So similarly, you have okay, so this should be Q uniform, and this should be hp dot choice. The choices will be the same, and this will come in the very beginning. Okay, and now we can have, for max features, you can have hp dot uniform instead of q uniform, and we take the max features from here and put it here, and everything remains the same. So is something wrong here? I don't know. It doesn't look like anything is wrong here. So now we have our optimization function, which is going to be the same. Instead of param names, we don't have the param names anymore, and we remove this one. And in our result function, so first we need to initiate a trial. So we will say trial is, or trials. Okay, so now you can have certain parameters there, but we really don't need it now. And result will be fmin, and then you provide a function which is your optimization function, and then you provide a space which is your parameter space. And you can also do you have to define trials, which is trials, and instead of n calls you have maxivals, which is 15. You don't have this verbose parameter, and what else do you need? Algorithm. So you also need what kind of algorithm you want to use. So we will use tp.suggest. Okay, and now here we can just do print result, and let's hope it works. Let's see. HP choice takes 2 positional arguments, but 3 were given. Okay, so that is a problem, and so that was the problem here previously. So you have to specify them in a list. And let's try this again. So n estimators must be integer got class float. So yeah, that is some of the problems here. So you need to fix that, and to fix that, what you can do is you can import scope from Hyperopt. So I think it's returning float values, and you have to just convert them to int. So from Hyperopt import scope. And here you just wrap this in scope.int. So this is something that you can do, and do the same for n estimators, and you're done. Okay, let's see. Cannot import name scope from Hyperopt. Oh, okay, yeah, sure. So it's not in Hyperopt. Hyperopt dot base import scope. Let's see. So we have 15 trials, and it has already reached 89.2% accuracy. So we just let it run for 15 and see what happens in the end. So it has finished now, and you can see it has found some optimal parameters. So criterion is 1, so it's 0 and 1. 0 was it's the index, so just have to remember that. 0 is entropy, 1 is 0 is Gini, 1 is entropy. And then you have the max step, max features, and number of estimators. So we have found the best parameters, and our accuracy is more than 90%. So it's awesome. And now there is one more very good library, and this is something that I have not discussed in my book. So that's Optuna. So we will be trying to use Optuna for the same thing that we are doing, and see how that performs. So Optuna is also a very good hyperparameter optimization library, and this is something that I have not discussed in my book. But I was recently talking to one of the core developers of Optuna, and he suggested me to take a look at this, and I did, and I found it very good. So let's see how we can use Optuna for the same function that we have been optimizing till now. So first of all, that you need to do is to import Optuna, obviously. So you can install it using pip install Optuna. And now we don't need so for Optuna you cannot define parameter space outside, so you have to define it inside. So you don't need this, and instead here I will just write study, like a study. So Optuna dot create study. So I can do direction equal to minimize here. So it will minimize the function. You can also do direction equal to maximize, and then you don't need to do the negative thing, but we have been doing multiplication by -1 for everything, so let's keep it that way. And here you can do study.optimize objective, no, optimization, optimize, comma, here you specify the number of trials, 10 or 15 trials. So now you go inside your optimization function, and here it will take okay, so we still need to create the partial function. So optimization function partial, and then you have x equal to x, y equal to y. Okay, and your objective function should take a variable argument called trial and x and y. So now you don't have params anymore. Okay, and x and y we have already defined, and instead of sorry, you need to write optimize here, and optimization function will be input to study.optimize. And here now you have to define what you're selecting. So the params, the grid that we have been defining till now, has to be defined inside now. Okay, so you can have something like entropy equal to trial dot suggest categorical, and inside that you can have different categories. What should I call it? Criterion. And inside that you can have Gini, entropy. Okay, and so this is like one of the things that you have now, but you have to also do it for int and integers and real number. So you can also do like an estimators is trial dot suggest int, and then you have an estimators, so any name that you want, and you can give a min and max value. So I can do number of estimators 100 to 1500. And what was the third thing that we had? So we had entropy, we had number of estimators, we had max depth, which is also your int, right? So you can do int, and we will use the same name here, max depth between 3 to 15. And there was one more thing, which was max features, and we can take it from suggest underscore uniform, so from a uniform distribution. So we can say max features equals sorry, this is name that you have, and then 0.01 to 1.0. And now, so you have defined every variable here, which is also very nice and compact, right? So you can do a lot of things here, and it won't be as complicated as Hyperopt. So by the way, Hyperopt is also not very complicated, so you can use anything you want. It just depends on your choice. So n estimators is n estimators, and max depth is max depth. And then what we have, max features is max features, and criterion is, so it should be, I should change the name Okay, so we have this, missing a comma, and that's all you need. So let's try to run it and see what happens. X is not defined. Okay, sorry. X should be capital. Let's see. Optimize got an unexpected keyword argument X. So this is small x. Okay, let's try again. So yeah, it is running finish trial 0, value 85, and then it's showing you criterion was Ginny and estimated was this, and blah blah blah. Again, it finished trial 1 with a value of 83.7, so it's negative because we are minimizing the accuracy, so you can directly do maximize if you want. But this is so cool. So I think I like Optuna more than anything else, and this is actually the first time I'm using it. So I think you can do a lot of things here. Let's go take a look at Optuna's documentation and see what you can do in the meantime. So they do have a website too. I think it was called Optuna.org. And yeah, so here they provide some examples, and which I think is quite nice. So you have an objective function and you're suggesting some uniform distribution. So let me increase the size for you, and you return something, and then you say if you want to maximize or minimize, and you have the number of trials. Awesome. And let's see the PyTorch thing. So what they are doing in define an objective function to be maximized. Okay, and then suggest the value of hyperparameters using trial object. So you have number of layers, so it's suggesting the number of layers, which is quite nice. And so this is how you can also use it for PyTorch models. So it's basically, in the end, it's just about a function, an objective function, and it should return some kind of objective value that you want to maximize or minimize. And it's the same for all kinds of hyperparameter tuning libraries, so you don't have to change a lot of stuff there. So let's take a look what's happening here. So it has reached 0.899. I think it's a little bit slow, or maybe it's the same, taking the same time probably. So anyways, it's reaching a value of 0.908, 90.8% accuracy, which is quite good. So now in this video I've discussed grid search, randomized search, I have discussed SK optimized, scikit optimized, I have discussed Hyperopt, I have discussed Optuna. So now it's up to you which method you choose. I like to try to tune hyperparameters manually first, and then choose a range of values, and then throw in some kind of optimization algorithm. So that's something that you can do, but it's totally up to you. I know it has been a little bit of longer video than usual, but I hope you like it. And if you like it, click on the like button and do subscribe and share it with your friends if you feel like they should also learn. I hope they will like it too. So that's it for today's video. If you have any suggestions or comments, do let me know. I won't be sharing the code on GitHub for this. Most of the code is also available in my book, so you can grab the book if you want. And it's more about learning by coding, so watch the video and code yourself. You will learn a lot more than just copy pasting code from somewhere. So thank you very much, and see you next time, and goodbye.